Good afternoon. I know it's 3:30 and we're diving in something pretty technical after a long tea break. But hey, if you're here, I guess you enjoy solving complex problems. So let's dig in and see how we can make sense of the madness together. But before we start, let's have a quick introduction. So my name is Alex, and I'm the VP product at Datorios. Over the past 18 years, I've been deeply involved in developing, implementing, and designing observability tools. Throughout my career, I faced countless challenges diagnosing real-time data processing issues, and I've spent years refining how we can quickly pinpoint the root cause of critical problems as they happen. Joining me today, my friend Colton.
Hi, I'm Colton Pilgreen. I'm the resident Flink expert here at Datorios. And whenever I'm not helping them, I'm actually the lead data engineer on the ad platform team at Hulu, where I handle everything from Flink to billing to real-time reporting.
Thanks, Colton. So over the next 28 minutes, we're going to show you a fresh approach to identifying root cause and analyze complex problems in Flink. One which is faster and a bit more user-friendly. So here's what we'll cover. We'll start with the need for visualization and why seeing is believing. Next, we'll speak about why visualizing Flink problems is different and a bit more complicated. We'll walk through some use cases and how they were solved manually. And finally, we will finish with how visualizing the data could solve problems faster. All right, let's jump in. But before we dive into Flink, let's talk about something fundamental. Why visualization is so crucial for understanding and diagnosing problems. Let's try a quick experiment. I want to see your hands. How many of you think that global warming is a real problem? OK, cool. I see some people raising their hands. Now, for the rest of you, either you're in a denial or you got some seriously impressive air conditioning at home, right? Now, take a look at this graph. At first glance, you can probably tell that something is happening here. There are trends, spikes, and lots of data points. But if I asked you to quickly explain what is going on, could you? It's packed with information, but not exactly clear, right? It's the kind of graph that makes you feel like you're missing the punchline. Let's take a look at another example. So here's a short video that shows global temperature trends by country over the last 100 years. The blue color represents temperature which is below the average, while the red one represents a temperature over the average. And here come the 80s, Industrial Revolution 3.0. Automation, computers, electronics. So you see this map, and now you can see that actually something is happening here. So unlike the last graph, where patterns were buried under a sea of data, this one distills and clarifies that something is actually happening here. So let me ask you again. After seeing the video, how many of you feel confident that global warming is a real problem? More hands. See the difference? When we just looked at the raw data, it was hard to get a clear picture. But once we turned it into a simple visual narrative, the message becomes much clearer. It's not just about presenting the data. It's about telling the story behind it. The challenge with data is that it's often overwhelming. In a system like Flink, there is so much data: logs, metrics, hidden metrics, which can be activated based on need. It's just hard to make sense of it all. Without a story to guide us, data can feel like noise. We need to take the data and turn it into something that is easy to follow and meaningful. So how can it be done? We suggest by data storytelling. So data storytelling is the process of turning raw data into a meaningful and actionable narrative. It's not just about showing numbers or charts. It's about making the data easy to understand, relatable, and insightful. A good story told by data will combine three key elements. So the first one would be data. The facts, the numbers, the trends, everything which provides the foundation for the upcoming steps. The second one would be the narrative, the story that gives the data context and meaning. The third one would be the visualization, which is the graphical representation that brings the data to life and make the story clear. So how a good data story will look like? It will simplify the complexity by breaking down complex data into something easy to understand. Engage the audience, make it relatable, so the audience connects with the story. And finally, and this is the most important one, it will guide decisions. It should help people make decisions based on the story you would like to tell. A great data story doesn't just show the data. It shows what the data means and what actions to take next. So diagnosing failures in Flink is not exactly straightforward, as it requires more than just logs or metrics because of some unique challenges that come with stream processing. So let's explore three key reasons why understanding or reproducing failures in Flink can be so difficult. The first challenge is that Flink often processes data, well, out of order. Events do not always arrive in the same sequence as they were generated. So when you are trying to figure out what went wrong, it's crucial to process the data in the exact same order as it was originally received. Without doing that, it is nearly impossible to accurately recreate the issue. The next one will be time. Time plays a crucial role in Flink's stream processing. Following the out-of-order data, the processing time can have a noticeable impact on the final outcome. So here are a few examples. A record could end up in a different window, be ignored due to latency policies, or be counted as a late arrival, which might trigger additional actions and consume more resources. This can even lead to a different final result. So without reproducing the exact timing, it's tough to understand what really went wrong. The third challenge, which in my opinion, this is the most challenging one, well, it's Flink state, which is, it's hidden. Each record interacts with it and affects the state, but there is no easy way to see how or understand what's being stored at any given moment. Without visibility into the state, it becomes super difficult to pinpoint how specific records contributed to a failure. So let's review some use cases where we met those scenarios in real life. Colton, could you share some?
Yeah, sure, why not? So let's get into the juicy stuff. Real-world problems that we've encountered while using Flink. Our first use case is the dreaded late data. This one's such a headache that it's drilled into your head from day one. If you've picked up a real Raleigh book, the first 100 pages are basically entirely dedicated to this. Use case number 2, runaway or unpurged state. This one's a doozy, especially if you're writing stateful process functions or custom window triggers. Use case number 3, incorrectly updating state. And I'll admit, this is actually on us as the engineer. We're the ones who are at fault here. But it still doesn't make us question our lives any less when we have to debug these. So how many of you have had one of these problems happen to you? Maybe all 3 at once?
I did.
You don't even write Flink pipelines.
I did.
All right, so on to use case number 1, late data. And I know what you're probably thinking, Colton, we know about late data, we handle it all the time. However, it's still one of the most common problems I see new Flink engineers face. The whole concept of 2 different types of time and watermarking is a tough thing to wrap our heads around. So what is it? Late data is pretty much exactly what it sounds like. It's just data that made it to our pipelines too late and couldn't be processed like on-time data. This occurs when 3 criteria are met. You're using a watermarking strategy with event time watermarks, you have a pipeline somewhere inside of your job, and you have out-of-order data. So how does it affect our outputs? This leads to incomplete and inaccurate window emits. This can actually lead to loss of revenue or other people's trust in your data. And the problem with this is it's actually silent by default. So if you're not actually checking if you're receiving late data, the problem's going to go unnoticed. So how do we know if the problem's even happening to us, and how do we become actionable on it? Well, the first thing you can do is you can actually create some custom metrics based on your late data site outputs from your windows. You can regularly conduct investigations into data source latency. And the most important one is actually to have conversations with your upstream providers. But what if there was an easy way?
Is there?
There is. So once you've got the Datorios telemetry collector up and running, you can actually load up your job and pull up the job inside screen. This page gives us an overview into which operators are inside of our job graph, how many records were sent and received, and the throughput of our operators. However, what we're actually more interested in is the window collector section at the bottom. If you look below, our windows received an average of 4 records per emit, and 60% of our records were ignored. This pipeline is supposed to receive records every 5 seconds, so that would actually mean about 12 emits per window, because we're rolling up to 1-minute windows. This kind of error rate means your data is completely unreliable. But we can actually continue our investigation by clicking the Ignored Records button below. So here we can actually see each ignored record that ever came out of our window operator. You can see the time it was ignored and the key that was affected. These screens are super helpful for verifying if we're even seeing the late data, but also finding out which potential records were affected. The best part here is actually requires no user code on our end, and we don't need to set up any of those pesky metrics or handle the data in any special way. We get these insights out of the box, the black box. So from here, we can actually go into the tracer screen. So this screen shows you a timeline of every event you received in the pipeline. If you look closely at the window operator, which is the 4th one down, or the 3rd one down, I think, yeah, you can see a lot of events outlined in red. And this means that they were late. And since they were late, they actually never made it into our window outputs. So we can drill down even further and select a window to investigate. And if you look way on the left in that graph, you can see one lonely event. Once we have a conversation about our data latency and fix our watermarking strategy, hopefully it'll have a couple more friends to be aggregated with.
Hopefully.
All right, on to something slightly more tricky. Runaway state, unpurged state, or sometimes it's just called state that's too large. So what is it? Runaway state's when you have state that's held by your Flink pipelines, but it becomes too large to be held inside of your memory or disk if you're using RocksDB. So there are several reasons why you actually might encounter runaway state. The data you're ingesting is simply too large to be handled by the state values you want to store. You're storing too much data, like a large list state, whenever you should have been storing, like a value state, and then just reducing down each event as it came in. Or the biggest one that I see, the most often with new engineers, you're just forgetting to clean up your state whenever you're finished using it.
Only with new engineers?
All right, so how does this one affect our output results? Well, the scary part here is that it's going to lead to those stupid out-of-memory errors. This means that your pipeline is going to halt entirely, and then you're not going to have anything to do until you scale up your cluster resources. In the end, this is a show-stopping problem. Your pipeline is going to cease to emit anything until you've handled it. So how do we know if it's even happening to us, and how do we mitigate it? Do you know? No? OK. So I actually kind of gave you the answer to this one. We know if we see a large uptick in those out-of-memory errors. But the problem here is we actually don't know if out-of-memory errors are caused by a runaway state or another issue. There's also not a great way to track state size with metric reporters. And you have to rely on half-baked solutions like looking at managed memory utilization. And even if that's high, it doesn't actually point to a runaway state. Or you can create custom metrics to track every single thing you're storing in state. But that's going to lead to really big cost and performance. But the thing is, what you really need here is a way to be able to view the state that's inside of our operators. The thing is, you can do that now. So what we have here is a different job. And we're back here at the tracer screen. So this pipeline is supposed to calculate the minimum, maximum, and average statistics for every temperature sensor sent. This is a fairly easy calculation, but I think the way that it was implemented here is causing our runaway state issue. So what is happening is we turn the job on, it runs for a bit, and then we see those pesky out-of-memory errors. And it happens no matter how many times we keep scaling our resources. So what we have here is our event timeline. So we're going to select the last record that our job could send before it crashed. And the relevant state is in the temperature metrics operator. And once ever we have those events highlighted, you can drill down even further and see the state investigation screen by clicking on the relevant record. So once ever you see the state investigation screen, we're presented with the incoming record in the middle, along with the state values on each side of it. To the left is a sample of what the state looked like before the record was processed. On the right, what the state looked like after the record was processed. So in our incoming record, we've highlighted the temperature reading, and you can see that it's about 30 degrees. So if we scroll to the bottom of our before and after states, you can see that the last held state in our before was 36 degrees. But in the after, it's now 30. That's what was inside of our incoming record. This means the temperature reading is just being added to our list state for every record that's coming in, and the calculation is being done on that list state. This is actually really inefficient. We could actually just hold a singular value state and reduce all of our incoming events into that value state. So the way it works now means that the state is growing up without bounds. And this would actually be the cause of our runaway state issue. And, that's not a good thing. All right, on to our final use case. And we're going to talk about its incorrect state updates. This one's a little different than the previous two we've talked about because it's directly caused by us, the engineer. I actually even make this mistake myself sometimes. I'm actually writing a different pipeline to showcase here at Flink Forward for our lineage session. Yep, it is our problem sometimes. All right, so what is this problem and how does it connect to us? Incorrect state updates is just when you're either updating state and you shouldn't be, or you are updating or purging state and you shouldn't. This is normally fairly easy to unit test using something like test harnesses, but it becomes tricky when we start chaining our operators together. So how does it affect our output results? Well, with this use case, there are actually many different ways it can affect our results. You could either be storing or including too much or too little data inside of your outputs, or it could be something as small as not registering a value state that's holding your registered timers, or as big as accidentally clearing an entire map state when you meant to be updating a single key. Which means you could actually be enriching data with entirely incorrect results. The possibilities are almost endless with this one, and just like late data, it's silent by default. So how do we know this problem is even happening, and how do we become actionable on it? So debugging these issues is actually kind of tough, and bad news for you, without being able to view into the state, it's kind of hard. Most of the time, there's actually not a way to monitor these kinds of issues, and you have to manually verify your pipeline's outputs. The best way to become actionable is actually to have good communication with your upstream providers, and to review your code to make sure you're handling all your edge cases. That means not just approving the PR that comes to your Slack messages. So earlier I'd said I actually made this mistake when writing another pipeline. So I'd actually written a compliance engine for a lineage session. I'd sent it over to our CEO, Ronan Corman, for verification. He did his investigation, and he found that I made a mistake.
Told you it's your fault.
It always is. So he opened up the records, and he noticed that I wasn't registering a timer state value. We were concerned something was off with the Datorios telemetry collector, but in the end, it was me. What was going on here is I had a broadcast process function, and it was matching policies to vehicle events. I was doing the match correctly, but I forgot to register the event timer and update the timer state. This just goes to show that even us who have been writing Flink pipelines for years can make the silliest of mistakes. And this mistake would have actually caused a runaway state problem eventually. And that one's kind of ugly. And if you don't believe me, here's the proof. Here's the messages that prove that even I'm not perfect. All right, take it away, Alex.
Thank you, Colton. Thanks for running us through the use cases. So let's wrap it up with some key takeaways. So the first key takeaway, which I would like you to take from here, is visibility is a key. Flink state and timing are hidden by default. You need tools that provide you visibility into how data is processed and stored to understand what is happening inside the system. Second one would be state and time. It's drive Flink challenges. The core challenges in Flink arise from its handling of state and time. Addressing this requires real-time insights. Data correlation and storytelling matters. Great observability tools connect the dots and tell the full story. And the last one, speed matters. Diagnosing Flink issues manually can take days, and it can be just frustrating. With the right tools, it might take you only several minutes. Oh, and what about the climate? Well, I don't have an answer for this one, or how to fix climate changes, or find the root cause for global warming. But what we can help with is improving Flink troubleshooting experience. If you're interested in learning more, come chat with us. We would love help you making Flink, more visible. Now it's your turn. Any questions, thoughts, or shared traumas from your own Flink adventures? Let's hear them.
Hey.
Hello.
Thanks for sharing those use cases. It was great seeing the visualizations that you've implemented. I'm wondering, how much of the instrumentation is done at the job graph level, and how much of it is actually done on the cluster?
So we're doing we basically expanded the Flink API to get us more information. So it's basically done in the engine itself, and it exports additional data, which eventually allow us to create those visualization and tell the story better. But by default, you just don't have some of this information in order to create the story. Anyone else?
Thank you for the presentation. So given that you're adding more stress on the on the infrastructure, how aggressive does it get, and does it actually turn out to be killing the entire job, or how do you handle that?
So basically, we have two mechanisms, which one of them is just broadcasting data out of Flink, and it won't probably send 100% of the data, because we don't want to affect Flink performance. So it will send pretty much like more than 95% of the data. And this would be enough to start troubleshooting and see the full picture. And all the performance is actually out of the Flink. Another process is usually something we use for specific debugging, but we will turn it probably for like several minutes only, and it will send each record exactly once. This will affect the performance around 10% by the troubleshooting we did. Here.
I would like to just understand what is the model exactly for running Flink applications for this use case. Does it mean, so you mentioned you've patched the engine. Does it mean that a custom Flink version has to be used?
Or we can just take, so basically we added the additional jars, which expanding the core functionality of the engine. So yeah, we need to patch the engine, or we have pre-prepared Dockers with every Flink version, just in order to make it easy on the instrumentation.
Okay, but it can be just an addition of jars onto the class path that would allow this instrumentation. Is this correct?
Sure,
that you can just add your jars with this implementation into an existing Flink release.
Yes.
And it will work. Okay. Got it. And from the platform perspective, is this something that you create an account for a platform, for instance, right? So does this mean that the job has to run on your infra, or how does it exactly work from, I have my job running on my infrastructure. How do I get those insights exactly?
So basically, we have several deployments. I can elaborate about that more if you like later, because we're running out of time. But basically, you have a Flink running in your environment, and we have OpenTelemetry collector, which is just sending data out of it. Now, the question where the data will be, or where will you see the visualization, I mean, it depends on the deployment. We have several ways to deploy the system. Just running out of time, so come to the booth, and I would be glad to share more about this.
Got it. Thank you.
Last question?
Yeah.
Okay. Thank you for the presentation. I also very like your T-shirts.
Come to the booth, I'll give you one.
Okay, got it. Question, using your tools, can we monitor also RocksDB?
Yes. We're doing it in a bit different way currently now from Flink. So we know what goes into the RocksDB. We added basically a trace ID for each one of the records. But we can present what happens in the RocksDB as well. So we can present what happens with the state for each one of the records before it get into a specific operator, and after it went out of that operator, or after it affected the state. So we did it for RocksDB as well. We have it in the demo outside, if you want.
Cool, thank you.
So thank you all, and have a good day.